Now, to understand the explain away effect, you have to compare this to the probability of a race given that we're just happy and we don't know anything about the weather. So let's do that exercise next. So my next quiz is, what's the probability of a race given that all I know is that I'm happy and I don't know about the weather? Now this happens to be, once again, a pretty complicated question. So take your time. So this is a difficult question. Let me compute an auxiliary variable, which is P of happiness. That one is expanded by looking at the different conditions that can make us happy. P of happiness given S and R times P of S and R, which is of course the product of those two because they're independent, thus P of happiness given not S R, probability of not as R, plus P of H given S and not R times the probability of P of S and not R, plus the last case, P of H given not S and not R. So this just looks at the happiness under all four combinations of the variables that can lead to happiness. And you can plug those straight in. This one over here is 1. And this one over here is the product of S and R, which is 0.7 times 0.01. And as you plug all of those in, you get, as a result, 0.5245. That's P of H. Just take some time and do the math by going through these different cases using total probability, and you get this result. Now, armed with this number, the rest now becomes easy, which is we can use Bayes' rule to turn this around. P of H given R times P of R over P of H. P of R we know from over here. The probability of a race is 0.01. So the only thing we need to compute now is P of H given R. And again, we apply total probability. Let me just do this over here. We can factor P of H given R as P of H given R and S, sunny, times probability of sunny, plus P of H given R and non-sunny, times the probability of non-sunny. And if you plug in the numbers for this, you get 1 times 0.7 plus 0.9 times 0.3. That happens to be 0.97. So if we now plug this all back into this equation over here, we get 0.97 times 0.01 over 0.5245. This gives us approximately, as a correct answer, 0.0185. And if you got this right, I will be deeply impressed about the fact you got this right. But the interesting thing now to observe is, if we happen to know it's sunny and I'm happy, then the probability of a raise is 14%, 0.014. If I don't know about the weather and I'm happy, then the probability of a raise goes up to about 18.5%. Why is that? Well, it's the explaining away effect. My happiness is well explained by the fact that it's sunny. So if someone observes you to be happy and asks the question, is this because Sebastian got a raise at work? Well, if you know it's sunny, and this is a fairly good explanation for me being happy, you don't have to assume I got a raise. If you don't know about the weather, then obviously the chances are higher that the raise caused my happiness, and therefore this number goes up from 0.014 to 0.018. Now let me ask you one final question in this next quiz, which is the probability of a race given that I look happy and it's not sunny. This is the most extreme case for making a race likely because I am a happy guy and it's definitely not caused by the weather. So it could be just random or it could be caused by the race. So please calculate this number for me and enter it into this box. Well, the answer follows the exact same scheme as before, with S being replaced by not S. So this should be an easier question for you to answer. P of R given H and not S can be inverted by Bayes' rule to read as follows. Once we apply Bayes' rule, as indicated over here, where we sort H to the left side and R to the right side, we can observe that this value over here can be readily found in the table. It's actually the 0.9 over there. This value over here, the raise is independent of the weather by virtue of our Bayes network, so it's just 0.01. And as before, we apply total probability to the expression over here, and we obtain of this quotient over here that these two expressions are the same. P of H given not S not R is the value over here, and the 0.99 is the complement of probability of R taken from over here, and that ends up to be 0.0833. This would have been the right answer. It's really interesting to compare this to the situation over here. In both cases, I'm happy, as shown over here, and I ask the same question, which is whether I got a raise at work, as R over here. But in one case, I observe that the weather is sunny. In the other one, it isn't. And look what it does to my probability of having received the raise. The sunniness perfectly or well explains my happiness, and my probability of having received the raise ends up to be a mere 1.4% or 0.014. However, if my wife observes it to be non-sunny, then it is much more likely that the cause of my happiness is related to a raise at work, and now the probability is 8.3%, which is significantly higher than the 1.4% before. Now this is a Bayes network of which S and R are independent, but H adds a dependence between S and R. Let me talk about this in a little bit more detail on the next paper. So here's our Bayes network again. So in our previous exercises, we computed for this network that the probability of a raise of R, given any of these variables shown here, was as follows. The really interesting thing is that in the absence of information about H, which is the middle case over here, the probability of R is unaffected by knowledge of S. That is, R and S are independent. This is the same as probability of R, and R and S are independent. However, if I know something about the variable H, then S and R become dependent. That is, knowing about my happiness over here renders S and R dependent. This is not the same as probability of just R given H. Obviously it isn't, because if I now vary S from S to not S, it affects my probability for the variable R. It is a really unusual situation where we have R and S are independent, but given the variable H, R and S are not independent anymore. So knowledge of H makes two variables that previously were independent, non-independent. Or put differently, two variables that are independent may not be, in certain cases, conditionally independent. Independence does not imply conditional independence.